two images side by side. They look identical. But the JPEG on the right threw away 61 out of every 64 numbers describing this picture. Your eye cannot tell. Here's how that's possible, and it comes down to one idea from linear algebra. Choose the right basis. An image is just a grid of pixel brightness values. JPEG chops that grid into 8 by 8 blocks. Each block holds 64 numbers, so we can treat it as a single vector, living in 64-dimensional space. Compressing the image really means compressing each of these little vectors. Here's the trick. In standard coordinates, all 64 numbers look equally important. But if we rewrite the very same vector in a smarter basis, most of its coordinates collapse to nearly zero. That is the entire game. JPEG is a 3-act play. Act 1, change of basis. We rewrite the pixel vector x using the Fourier basis, producing 64 coefficients C. This step is lossless and fully invertible. No information is lost yet. Act 2, thresholding. We look at the coefficients, keep the biggest few, and set the rest to 0. This is where information actually disappears and is the only lossy step in the pipeline. Act 3, reconstruct. We rebuild a full 64-pixel block from only the surviving coefficients. The output is still 64 pixels. It just took far fewer numbers to describe. Change of basis is just rewriting the same vector with a different vocabulary. The Fourier basis for an 8 by 8 block contains 64 pattern vectors. The first is constant, pure average brightness. Later ones are increasingly wavy. The last is a checkerboard, alternating +1, -1, the highest frequency you can fit. Every block is a weighted sum of these patterns. The coefficient C sub k tells you how much of pattern k is present. No information is lost. We just change coordinates. Now the magic. Natural images are smooth. The average brightness coefficient is huge. Low frequency coefficients are moderate. High frequency coefficients, the checkerboard and its neighbors, are almost always near zero. Your visual system literally cannot perceive those fine oscillations anyway. So we threshold, zero out everything below a cutoff. Suppose only 3 coefficients survive, the constant term and 2 low-frequency partners. We've replaced 64 numbers with 3. The high-frequency information is gone forever, but it carried almost no energy and no perceptible detail. The lie is invisible. Reconstruction is just a change of basis run backwards. We combine the 3 surviving basis vectors, weighted by their coefficients, and out pops a full 64-pixel block, visually indistinguishable from the original. 3 numbers stored, 64 numbers reconstructed. That's roughly a 21:1 compression ratio. Scale this up across an entire photo, and the multi-megabyte raw image collapses to a few hundred kilobytes, with no visible quality loss. So Fourier wins. But is it the best basis we could pick? Fourier patterns stretch across the entire block. They describe frequency perfectly, but they have no sense of location. A sharp edge, a fingerprint ridge, a black to white boundary forces Fourier to use many high-frequency coefficients all at once, killing the sparsity that made compression work. Enter wavelets. Wavelets are basis vectors that localize in both space and frequency. They know where things happen, not just how wavy they are. Here's the full hard wavelet basis in 8 dimensions. The first vector is all ones. That's the average, the scale 8 piece. The second is +1, +1, +1, +1, -1, -1, -1, -1. It compares the left half to the right half at scale 4. The next 2 split each half again at scale 2. The last 4 are the finest detail. Each one is +1, -1 on just 2 adjacent pixels, 0 elsewhere. 1 vector at scale 8, 1 at scale 4, 2 at scale 2, 4 at scale 1. Multi-scale structure baked directly into the basis. Wavelets and Fourier span the same space. They're just different vocabularies for describing the same vectors. Watch this. Take the Fourier checkerboard. 1 minus 1, 1 minus 1, 1 minus 1, 1 minus 1. Now add the four finest Ha wavelets. The first is 1, minus 1, 0, 0, 0, 0, 0, 0. Add to it 0, 0, 1, minus 1, 0, 0, 0, 0. Then 0, 0, 0, 0, 1, minus 1, 0, 0. And finally, 0, 0, 0, 0, 0, 0, 1, minus 1. Component by component, the sum equals the checkerboard exactly. One basis describes this signal with a single global vector. The other describes it with four local pieces. Same vector, two vocabularies. Same space, different strengths. Fourier coefficients are global, perfect for smooth regions like skies and skin. Wavelet coefficients are local and multi-scale, perfect for sharp features like edges, text, and ridges. JPEG uses Fourier-style cosines. JPEG 2000 uses smoother wavelets. Neither is universally better. Choosing a basis is choosing what kinds of structure you want to capture cheaply and what you're willing to spend more bit on. This isn't theoretical. The FBI maintains tens of millions of fingerprint records. In the 1990s, storing them as raw images was impossible, and searching took weeks. They adopted a wavelet-based compression standard tuned for ridge patterns, shrinking each fingerprint roughly 15 to 1 with no loss of identifying detail. Searches that once took weeks now finish in minutes. Same idea as JPEG, different bases chosen to match the structure of the data. That's the lesson worth keeping. Linear algebra is an abstract bookkeeping. A basis is a language. Pixels speak the language of position. Fourier speaks frequency. Wavelets speak scale and place. Compression, and a lot of modern signal processing, is about translating your data into a language where most of what it says is silence.